Hey, so we're live. All right. This week is thermochemistry, continuing to do the stuff from Chapter 8. It's a little bit beyond what I know I've covered in lecture, but it's not too far beyond. It should be quite doable. So, what you're going to be doing is you're going to be finding the enthalpy changes of a couple of different things. First, you're going to find the enthalpy change for dissolving a couple of different salts in water. And then you're going to be finding the enthalpy change associated with some neutralization reactions. When a salt dissolves in water, it's sort of a multi-step process where you have to pull apart the ions in the salt. Then you have to pull apart the molecules of water so that you can insert the two among each other. And then the third step is mixing the two things together. I mean, this all happens all at once, but we can divide it up in that way. So that is what they're showing you here. Namely that the change in enthalpy for the whole process is equal to the amount of energy associated with mixing the salt into the water, here, the enthalpy of hydration, minus the amount of energy you have to put in order to pull the ions apart. That's this guy right here, the enthalpy change associated with the lattice energy. So whether dissolving a salt is exothermic or endothermic depends on the amount of energy you get back out, the enthalpy of hydration, versus the amount of energy you have to put in, the enthalpy of lattice energy. So, hopping over to the document, that's what you're going to be looking at here. Just initial temperature, final temperature, change in temperature. And then that is going to tell you whether it's an endothermic or exothermic process. Then that will also tell you which is greater, the enthalpy of hydration or the enthalpy of the lattice energy. Okay. You're going to have to do a little bit more math work for the second part when you find the enthalpy for the neutralization of a reaction. Because first you're going to have to, oops, that's not the one I wanted. This is the one I wanted. All right. First, you're going to have to find the standard enthalpy of the reaction using Hess's law. Okay. So what you're going to do is you're going to use the enthalpies of formation, where you take just pure elements and you mix them, you do a chemical reaction in order to make the substance as it is. So let's bring up the thing. So for example, the enthalpy of formation for hydrogen chloride would be H2 plus Cl2 yields HCl, aqueous. And that has an associated enthalpy of formation shown in the table that you can see on the right. Negative 167.2 kilojoules per mole. You cannot see any of what there we go. So that is the form of an enthalpy of formation. The way you use this is, coming back over here, you can still see it. Okay, it says delta H of reaction is a complicated looking formula. What this means is you use the enthalpy of formations, you find the enthalpy of formation of all your products and all of your reactants. You're going to multiply them by the number of moles in the balanced equation. That's what the N there means, is what is the coefficient. You multiply the coefficient times the enthalpy of formation for each product. Then you add all the products together. That's what this guy here means, the Greek letter sigma. Then you do the same thing for all the reactants. Multiply the number of moles in the balanced reaction, multiply that by the enthalpy of formation for each reactant, then you add all of those together for the reactants, and then it's products minus reactants. It's a very, very straightforward sort of thing. And when you do that, that will get you the standard enthalpy for the reaction that you're going to be comparing your experimental values to. So after you have those standard values to compare to, you're going to, I'm back here, you're going to run a couple of trials for hydrochloric acid and sodium hydroxide, and then a third trial for acetic acid and sodium hydroxide. Oops, you can't really see that because it's boop. All right, so for those simulations, you're going to assume you have a nice perfect calorimeter, and you're just going to record the temperature changes for each of the reactions. And they tell you the total solution mass for each one, and they give you the specific heat capacity for the calorimeter. You'll notice it is slightly different from the specific heat capacity of water because there's stuff dissolved in the water, and that's fine. And then using the regular heat equation, remember, Q equals mc delta T, you're going to use that to get what they have identified here as delta H in kilojoules. But remember, you have to normalize it, generalize it. So it's not just, you're not looking for the enthalpy of this particular reaction so much as you're looking for the enthalpy of the reaction as a whole, generally speaking. So you are going to have to divide by the number of moles of the limiting reactant. In this case, it won't really matter which one you pick. They'll both be the same number of moles, and there is no limiting reactant. They're present in equal amounts. So once you divide by that, you'll have the enthalpy of the reaction, generally speaking. And then this is the enthalpy of reaction from Hess's law. That's the one that you calculated first, products minus reactants. So you're going to compare this one here, the enthalpy of reaction you found using the simulation. You're going to compare that to this one, the one you found by calculating it from the table. And that's where you get your percent error. So it's kind of unfortunate that you don't get to do any calorimetry in class or in lab, but this will give you something of a feel for the hands-on work. It's just recording the temperature change, getting the enthalpy, this guy here, the Q of the reaction, then normalizing it, generalizing it to the reaction as a whole by dividing by the number of moles. Just go ahead and do it for sodium hydroxide. Choose sodium hydroxide, and you'll be fine. You have to now notice that this is a concentration, so that is not the number of moles of sodium hydroxide. You have to multiply moles or concentration times volume. Remember, number of moles is equal to concentration times volume. So you have to use that to get the number of moles of your sodium hydroxide. And then it's just this guy divided by, then it's just going to be this guy divided by the number of moles, and that will get you this number here, the delta H of reaction. All right, so this is not horrifically complicated. For the first part, you don't even need to actually calculate the enthalpy. You were just looking at the temperature change and judging is it endothermic or exothermic, and from that, you know which one of these is bigger. If it's exothermic, enthalpy of hydration is bigger. If it's endothermic, the enthalpy of the lattice energy is bigger. So, pretty simple. The second part, you're going to have to do some genuine math, but I don't think it's particularly difficult. You should be able to handle that fairly well. And with that, I have run out of things to talk about for this particular lab. I'm not going to throw... we covered most of this stuff in class, at least I have, in the first half of Chapter 8, so I think you will be fine. So, good luck. Remember, give yourself plenty of time to get this done. It'll take you a little while. And I'll see you around.